we're gonna take a look into a really interesting example. Basically, we're gonna be working with a data set that contains GRE, GPAs, and the prestige of the undergraduate institution for individual students. And we want to understand how these three independent features affect the admission into graduate school. This is a binary classification problem because we are looking into either the person is admitted or not, okay? And we have three different features. Okay, so the first thing that we need to do for this example, as usual, we are going to load a couple of libraries that we'll be using, namely AOV and ggplot. So let's load those. Okay, and once we do this, we need to load the file we're going to be working with, a CSV file called binary.csv, and it basically contains it contains a data set with students, and for each student it contains the GRE and the GPI information for each individual, the ranking of the undergraduate institution they attended, that's a number from 1 to 4, and then finally whether that student was admitted or not to graduate school. So let's try to load that file. We're going to call it my data, read.csv, binary.csv. Okay, and then we can view my data. And it's basically this table here. So again, 400 different entries. Each entry is one student, and you have admission decision, GRE, GPA, and rank. GRE and GPA are continuous variables. Admission decision is a binary value, but the ranking, it's a number, but we want it to be a category, right? And so what we need to do, as you very well know at this point, is to basically change the rank to be defined as a factor, right? And so we apply the factor command. We can just see the top of the data, but you know it should exactly be the same. Okay, it's exactly the same data set, but with the ranking defined now as a factor. Now, what we want to do, the first thing that we want to do is build a logistic model. Okay, in order to do that, we basically use a very general function in R called GME, which allows us to model different things. In fact, where you see there, the family feature there basically allows us to specify, you know, what exactly do we want to learn. In this case, what we are saying here is, let's apply GLM to run logistic regression, okay, with my data. And what we want to learn is admit, which is the dependent variable, and we want to see how this dependent variable can be obtained using GRE, GPA, and the rank of the undergraduate institution. Okay, so I'm calling it my logit because it's my logistic model. We use GLM, and we want to predict admit using GRE, using GPA, and using the rank. The data that we're using is my data, and specifically, we want to run a logistic regression. Okay, so if we type now my logit, okay, we get, let me close this, we get basically here, first thing that you see here is the call that you've made, so GLM with all the details that you've put. And here we see information about the model. Okay, so similarly to linear regressions, what you're seeing here is where's the location of the intercept and what are the different weights for the values that we have defined, for the independent features that we have defined. Okay, and this is exactly all the process that we mentioned before about learning the weights, about maximum likelihood estimates and so on. That's what has been going on when we call the GLM function with the binomial family. And this is the result. You can also check, let's see, summary. If you write summary, it's even more interesting, okay, because you can not only see the weights, but you can also see the significance that each feature has with respect to the final class. So in this case, remember, we are running a logistic model, and we want to learn or we want to classify whether a student is admitted or not. Okay, But what's the importance of each feature into the admission decision? So you can see that all features, the GRE, the GPA, and ranks 2, 3, and 4, okay, if the institution is of rank 2, 3, or 4, the GRE and the GPA values all are statistically significant, with more or less significance, okay, based on the asterisks that you see here, but they are statistically significant. This means that they have a say with respect to the admission decision. So this, by running this model and by taking a look at the summary, you can also understand what's the importance in terms of determining the admission decision, what's the importance of the different features that we are considering. And if, for example, in your models for your projects, suddenly you see that, a given feature has no statistical significance, you know that that's a feature that maybe you don't want to keep in your models because it's not significant and it's not contributing with any information, at least for the classification problem. Another thing to look at, basically, when you see these numbers here, okay, we've been looking into the asterisks, but the coefficients that you see, okay, what the coefficients are actually telling us is the change in the log odds, okay? So say for every unit change in a given feature, what are the log odds of the final decision, in this case of the admission decision, of the final label? Okay. It's a way of interpreting how does a change in a given independent feature, how does that change affect the final class? Okay, in our case, the final decision of accepting or not, but it could be something else. Okay, so another interesting thing, this is more of a curiosity, but I mean, if you're interested, we can also exponentiate the coefficients, because for some people interpreting log-odd ratios is not something natural, so we can also exponentiate the coefficients in the model, okay? And then basically, if you take a look at this, what we are looking into here is basically we can interpret this as 1 unit increase, by 1 unit increase of for example GPA, okay, the odds of the student getting admitted into the graduate school increase by 2.23, or for example for the case of GRE, by 1 point increase in the GRE, the odds of being admitted into the graduate school increases also by approximately one unit. Okay, I mean, so in this case, I mean, the coefficients are the same. Okay, so if you look at the coefficients here and the coefficients here, they're expressing here, sorry, and here it's exactly the same, but here, I mean, this 0.002 represented the log odds, whereas here this 1 is basically the odds without being logged. In any case, I mean, these are just nuances of how do we interpret the information, but by taking a look at the summary, we can figure out, first thing, what's the statistical significance of different features, and second thing, what does an increase in a given independent feature, how does that impact the odds of getting one or another label in the final classification problem. You can also compute confidence intervals. Okay, there's a command to see that if you're interested in that too. I mean, you can just try it and see the results. It's just the confidence intervals of the model that we have computed, and of the odds of different things changing, of the coefficients of different things changing. Okay, so for the sets of coefficients that we have described, what are the confidence intervals for those estimations? Imagine that we want to understand, for the model that we have built, okay, given this GRE, this GPA, and a given rank, what's the probability that that person is going to be admitted? Okay, so there are a couple of things to carry out this analysis. Obviously, what we need to do is use the predict function, as you see there in the second line of code. The predict function, what it does is that it uses the logistic model that you have computed on the data that you specify, okay? And basically, what it does is that given a data set, a test data set, what it does is that using the logistic model, it gives out what are the probabilities of those events happening. Okay, remember that logistic regression is a type of discriminative classifier that what basically does is it learns the conditional probabilities. Okay, so what this is going to learn, or the probabilities that it's going to output, are basically the probabilities that, given that set of features, what's the probability that the student is going to be admitted or not. And those are the ones that we want to be looking into. Okay, the independent variables that we want for our test data set is what we build with the first line of code there, with the new data one. The new data one, what it's doing, basically, it's the with command is taking the data set that we have, okay, and it's creating a new data frame that basically contains, for each rank value from 1 to 4, for each ranking of an undergraduate university, it's going to assign the average GRE and the average GPA from the data set that we have. Okay, so we are saying, imagine that we have a student that comes from an undergraduate university ranked 1 with the average GRE and the average GPA in the dataset that we have. And same thing for all the other rankings. What's the probability that this average student is going to be accepted in the different graduate programs based on the features that we've described? Okay, so let's do this and see what we get. Okay. Make this. Okay, so the first thing, as I was saying, that we need to do is basically we need to create the data set. So let's call it the new data, and we are going to use the data set that we have, and we are going to create a new data frame that has a GRE defined. A new data frame that has the GRE defined as the mean GRE, that has the GPA defined as the mean GPA, that has a rank value defined as what we've defined as a vector, right, with values from 1 to 4. Okay, we take a look at this new data. It's a data frame, exactly what we wanted to create. The last column is the rank defined as a factor from 1 to 4. And then the first and second columns are the mean GRE value from the my data dataset that we loaded, and the mean GPA value. So now we want to understand what's the probability that a given student that comes from a ranked 1 undergraduate university with the average GRE and GPA will get into a graduate program, and the same thing for all the other students with the different rankings. Again, this is a prediction problem, okay? So what we want to get is using the first thing that I wrote is basically we want to add a new column to the new data frame that we created to new data 1. We are adding a new column called rank P, and that rank P value is going to contain the probability that that student is going to be admitted. And basically that probability we can compute it using the logistic model that we have computed, and specifying that the input to the logistic model is going to be the new data and the type is going to be response. Okay, so if we take a look at new data $1 rank P, if we can take a look at this, what do we see here? So basically these are the probabilities, right? What the 0.51 means is that the probability of a student coming from an undergraduate institution ranked 1 with the GRE and the GP, the average GRE and GPA values that you see there, the probability of being accepted is 51%. Whereas a student with exactly the same GRE and exactly the same GPA, but coming from an undergraduate institution ranked 4, the probability of being admitted into a graduate program is 18%. Okay? So this is interesting in two directions. One, because it's telling us what we saw before, that the ranks are highly statistically significant with respect to the final classification. In fact, the ranking of the undergrad institution is highly important to determine whether someone is accepted or not, and it's more important than the other two, because in fact we see that students with the same GRE and the same GPA do not have the same probability of being accepted. So basically what this is confirming the results that we got from the summary of the logistic model, saying that rank values are really, really statistically significant. And we can play around, with these, trying other things. So for example, in this case, we have selected to have an average GPA and an average GRE, but we could also try and see, okay, what's the impact that having different types of GRE with an average GPA and with different rankings has. And this is what the rest of the slides for this example are doing. Okay, so if you take a look at this slide, it's basically creating, it's in the same philosophy of the previous example. This is basically creating a new data set, a new data frame, sorry, but instead of computing for each rank, we are going to have, the average GPA, but for each rank, we are going to have 100 different points, okay? And these are going to be various GRE values from 200 to 800, okay? And they go in fours, so we'll have 200, 204, 208, and so on, okay? And we repeat that again for each factor and for an average GPA. And what this example is going to allow us to understand is, given a certain GRE, okay, for an average GPA, what's the probability that that person is going to get accepted into graduate school or not, depending on the ranking of their undergraduate university. So let's create that data frame, and then let's, what we'll do is basically create the data frame, and then we'll apply exactly the same thing, the predict function with the new data set that we have created, and we'll try to see, what we're getting. So let's, in this case, create, I'm going to reuse some of the code that I have here. So let's create a new data, which I'm going to call new data2. I'm exactly going to run the example that you see in the slide, right? So you have new data2 with my data, but in this case, the data frame that we are creating has an average GPA, has a rank factor, but in this case, the GRE is going to be a sequence. So we are going to get a sequence that goes from 200 to 800 with a length of 100. This is for the sequence, we do it 4 times, and then we have the GPA. Okay, yeah, that looks fine. Okay, this is exactly the data frame that we have created. So we have created a data frame that has a rank for each ranking value. Let's view it all. So for each ranking value, okay, we are defining the same GPA, which is the average GPA from the original data set, but we are defining different GRE values, exactly 100 different GRE values in steps of 4 units. Same thing for ranking 2. We have average GPA, but we have GRE values from 200 to 800, and we have exactly 100 more, so it goes all the way to 200, and so on. Okay? Is it clear? Okay, so why have we created this data frame? Again, because we want to be able to understand what's the role that GRE, GPA, and ranking have in the admissions process. Okay, so this is a testing data set that we have created. We want to predict what's the probability of being accepted into a graduate program given these different GREs and GPAs values and different rankings of the universities. Okay, so we can use the predict function, but in this case, the new data that we are creating, let's look into the example. What I'm doing is exactly this one here. Okay, so I'm just using, again, it's exactly the same thing, the prediction function with the new data. So what I'm doing is I'm creating here a new column, which is ranked P, and the rank P is going to contain the probability of that individual being accepted into a graduate program. Okay, so if we take a look at the data, this rank P column is exactly a probability value. Okay, understanding it before, because we only had 4 points, was pretty straightforward. This is a little bit more complex, so what we are going to do is to plot it. You can do this in R. I'm just going to explain the plot that we get here. So what we see here, okay, this is the result of plotting the result from using the logistic regression model to predict the probability of a student being admitted or not with the new data frame that we have created, with the new data2. Okay, so the x-axis has the different GRE results, and the y-axis has the probability of that student being admitted into a graduate school. Each color represents a ranking. What this is showing is that the probability of a student from an undergraduate institution which is ranked, in the top undergraduate institutions in the country, independently of the GRE, the probability of that student being admitted into the graduate program is going to be higher than, if you come from any of the other undergraduate institutions. Okay? Even independently of the GRE. Okay? It doesn't matter. If you have a GRE of 200, but your undergraduate institution is ranked 1, the probabilities bump up basically from whatever, from 0.5 to 0.3, just because of your undergraduate institution. Okay? And this even goes, we see exactly the same reasoning here for the top GRE value for 800. If you have a GRE of 800, the ranking of your undergraduate institution changes your probability of being admitted from approximately 0.25 to over 0.6.